Geometric Brownian motion. We're still in the Ito's lemma section here because this is going to be another example of using Ito's lemma, but this is also an important process in its own right. Geometric Brownian motion is used as a model for the price of a risky asset. Here it is, it's a stochastic differential equation. It says we've got an Ito diffusion xt whose drift is a multiple of itself, so r times xt, and whose speed is also a multiple of itself, sigma times xt. Here r and sigma are constants. Okay, let's first, just to understand this, look at what happens when sigma is 0. Because that's a case that we should recognize. Then we've just got this, no random fluctuation at all, which means that the function we're looking for, xt, is just a function of time. As long as the starting point is not random, the initial value, then this will just be a non-random function of time. And what function will it be? Well, it's going to satisfy this equation. Its derivative is a multiple of itself, which, if you've ever seen a differential equation, you've probably seen this one. This is the one for which the solution is xt is whatever its initial value was times e to the rt. And you can easily verify that by differentiating this function, and sure enough, its derivative is r times itself. In financial terms, this equation, the one with sigma being 0, this is the equation that describes compound interest. If x0 is an amount you put into a bank account at time 0, then xt is how much you've got in the bank account at time t, allowing for interest being added and interest on the interest and so on, right? Compound interest. So it grows exponentially. Of course, exponential growth also models many other things, but in particular it models that, models interest in the bank. So, having understood that, now we can go back to the full equation and we can kind of see what's going on here. We've got a function that will describe the value of something, not necessarily a bank account now, which also grows in proportion to itself. So it's something that generates value just by being there, much like a bank account does. But it has some random fluctuation as well. So now we're thinking of something like price on a stock market. Or some other risky asset where the price fluctuates in a way according to some random driving process, which is the Brownian motion Wt. When I first started writing down Ito diffusions like this with a drift and a speed and a Wt, the way it was presented was that Wt is something that comes out of the process itself. It's like a sort of standardized version of the fluctuations of the process. But you can also think of it as Wt was what was there first. We started off with a Brownian motion, and then we construct this other thing, xt, that satisfies this equation, such that the internal Brownian motion of the process xt will be Wt, the Brownian motion we first thought of. So you can have that either way. Either xt comes first and Wt is something you extract from it, or Wt comes first and xt is something you build out of it. Then W is the driving Brownian motion of the process x. Alright, well let's solve this equation, the full equation. Again, I'm going to solve it by knowing the answer already and just substituting in to see that it satisfies it. So here is the full solution of the geometric Brownian motion equation. Xt is what it was to start with, times e to the power of that. So you can see there's an e to the rt in there, but actually it's e to the something t as well. There's minus half sigma squared, so sigma is having some sort of effect on the growth rate. In fact, it's reducing the growth rate. So if you have random fluctuations, the first thing that tells you is that in some sense it reduces your growth rate, but more importantly it also adds random stuff into the growth. Alright, that is the solution. Let's verify that it satisfies the equation. Actually, we'll go a step beyond that. Rather than just taking this as the solution, we'll say, suppose we didn't already know this, or not exactly, how would we tackle this? We would try for a solution of a particular form something like that. So here's the idea that Wt is something we've already got. What the Ito diffusion xt is going to satisfy the equation. Well, what's it going to be? You know, what could it possibly be? This explicit solution we're looking for. It's probably going to look something like a function of Wt, and maybe also a function of time. And if we do know the exact solution, we can see that, yeah, it is of that form, but even if we didn't know it, we could probably guess that it's something like this for some function h. And now we just have to find out what h is. So this would be where Ito's lemma comes in. We're going to apply Ito's lemma, which is made for things that look just like this, and see what Ito's lemma has to tell us about it. So Ito's lemma says that dxt is that plus that plus a second order term like that, involving the quadratic variation of Wt. Now actually we know that the quadratic variation of a Brownian motion between time 0 and t is just t, so we can immediately simplify this. It's like that. And we're trying to make xt satisfy this equation. So what we want is for this thing to be that, rxt, and for the thing that goes here, the hw, to be sigma xt. So these are two equations that we can hopefully solve to find out what h is. Once again, I've said this before, but I'll say it again, when we write things like ht and hww, these are the partial derivatives, and we're not doing this to save space, but it's understood that these things are to be evaluated at the point twt always. So, alright, let's take the second one first because it looks a bit simpler. What we need is I'll call this 1 and this 2. So, from equation 2, the HW, now I will put in the T and the WT, must be equal to sigma xt. That's to say, it must be equal to sigma times h of t and wt. So what are we looking for in the function h? It doesn't really matter that the wt is a random process now. In terms of a condition on h, this is what we're looking for. h should be a function so that when you partially differentiate it with respect to its second variable, you get sigma times the function you first thought of. And what sort of a function could that possibly be? Well, there are not many things that you can differentiate them and get back a multiple of the function you had to start with. It must be basically something like this, right? So that when you differentiate it with respect to w, you get sigma times itself. There can also be another part that depends on t, and that would just carry through as if it were a constant when we differentiate it with respect to w. So what we're looking at for h overall is something that looks like this. It must be some function of t times e to the sigma w. Now let's take this back to our first equation and see if we can use that to figure out what g is. So our first equation says that ht plus half hww should be r times h itself. So there that is written out in full. Or, since it doesn't really matter that wt is random, we're just looking for this as a property of the function h, we can just write this. H needs to be a function so that its partial with respect to t plus half of its double partial with respect to w is equal to r times itself. We have already established that h looks like this, so what we've got to look at now is, now we're looking at the partial with respect to t, so that's g primed of t e to the sigma w plus a half of, now we're taking the double partial with respect to w, so that's sigma coming out twice. Should be equal to r times h itself. Alright, we've got e to the sigma w everywhere, so they all cancel. So what we're looking for is a function g, so that g primed of t must equal this multiple of g itself. Alright, well we know this one. This is just the basic exponential differential equation again. It means that g of t is whatever it was to start with times e to the power of that times t, that constant. And therefore, putting it all together, what's h? Must be that times e to the sigma w, which is what we claimed it was in the beginning. You've got this exponential thing. The g of 0 here is also the initial value of h, of the whole thing, because the rest of this is e to the power of stuff, so when t is 0 and w is 0, remember the Brownian motion starts at 0, that will all be e to the 0, which is 1. So this is our solution. And that's the geometric Brownian motion. It's a very important process. We'll be using it a lot.